Okay. All right. Welcome back, everyone. Let me begin by asking if there are any questions on last time that you did not get a chance to ask during the Q&A.
I actually had a question about conifolds.
Yeah.
So is it true that anytime you have a conifold that has like a gravitational theory on it, that should be dual to a CFT? Or is it in like just...
No, not necessarily.
Okay.
For example, if you so it's an interesting question, which gravitational theories, which gravitational solutions admit a CFT dual, and not all of them will, and conifolds are not necessarily special unless you imagine that you got the conifold by taking some kind of a quotient of a theory that you know for sure had a CFT dual.
I see.
So you have to be assured in the beginning that your solution has a valid CFT state dual to it. Because you imagine I can take some crazy solution dash that equation with ridiculous matter, like a big rip singularity, and that's we don't expect that's going to have a CFT dual.
Okay.
Other questions? All right. So let's just remind ourselves that last time we talked about the covariant version of the holographic entanglement entropy prescription. So I'll just quickly write it down. Covariant holographic entanglement entropy. So we had the von Neumann entropy of the reduced density matrix on R equals to the area of an extremal surface over 4G. And by extremal surface, we mean two equivalent definitions. You could write it down in terms of the induced metric on the surface, which satisfies this equation. Or equivalently, you could say that the variation of the area of XR, d of the infinitesimal variation, d lambda v equals 0, where lambda v is parametrizes an infinitesimal deformation in some normal direction v. Okay, so this statement is just a statement that the in any variation of the surface, of the location of the surface to leading order in the perturbation is going to not change the area. Subleading order is a different question, but to leading order, it won't change the area. And this is literally saying the same thing. You can link these two by looking at, by rewriting this and toward this in terms of the lead derivative in this v direction. Now, one thing which is different from an assumption that we have to make for the covariant version that we did not need to make in the static case is the null energy condition. If you recall, I said that we are assuming the null energy condition holds, so we assumes null energy condition. So that's TAB, KA, KB is greater than or equal to 0 for all null vectors KA. Sometimes we write this as RAB just because we don't want to assume anything about the Einstein equation, but really we're going to be assuming this is the Einstein equation is satisfied in the bulk, and therefore the null energy condition is the same as the so-called null convergence condition. We also discussed the causal wedge inclusion. So this was something that was proved by Wall in 2012 and by Hedrick, Rubini, Lawrence, and Rangamani in a different way in 2014. And it's the statement that the extremal surface, or in fact, any extremal surface that's homologous to the region R is going to not be able to causally communicate with R. So XR lies out of causal contact with D of R. In terms of pictures, this is D of R. This is the boundary of the causal wedge. Then we expect that XR lies somewhere in this region over here. So this was in some sense a sanity check. Being able to prove this just using geometry is a sanity check on this proposal, because the reason that we must have causal wedge inclusion is that if we didn't, if XR were to lie somewhere here, then it would be possible to modify the area of XR by some local operator, which we could take to be a local unitary. And if we could modify the area of XR with a local unitary, then we would have a real problem, because we know that the von Neumann entropy is invariant under unitary transformations of rho sub R. So since we're doing sanity checks, we could ask, all right, so it satisfies this one sanity check, but what about other sanity checks? And the sort of next most obvious sanity check is to ask, does this satisfy strong subadditivity? But another thing, we want to show that these surfaces will satisfy strong subadditivity from some geometric principles, so that we were guaranteed that the quantity that they compute, the von Neumann entropy, also satisfies strong subadditivity, which we know must be true. And in fact, there is an open question here. I believe it's an open question. Somebody correct me if it's been solved since I last checked the archive. How to prove strong subadditivity in broad generality using the extremality criterion formulation. As far as I know, this has not been done. And in order to prove strong subadditivity, we actually have to go to a different formulation of the holographic entanglement entropy proposal, which was formulated by Aaron Wall, the so-called maxi-min formulation. Now, you might ask, and you would be well, you would be well posed in asking, why is it so much harder to prove strong subadditivity for the covariant case when it was so easy in the static case? It was just adding and subtracting, adding pieces of surfaces to one another. Why is it so much harder in the covariant case? And the reason it's so much harder is that it is no longer guaranteed that the extremal surfaces of A and AB and ABC and BC and AC all lie on the same Cauchy slice. And once they don't all lie on the same Cauchy slice, how are you supposed to be comparing their areas? How are you supposed to be adding and subtracting pieces of the areas when you can't put them all on a single Cauchy slice? So the reason that this is so difficult is because surfaces do not necessarily all lie on a single space-like hypersurface. And this is really where the power of maxi-min is going to be critical for us. So are there any questions so far on sort of the intuition behind why the difficulty comes up? I mean, let me just draw a quick picture here. So if you imagine here's a boundary region R, and we have another boundary region R prime. So this is R prime. Then we have this extremal surface of R, and this one might be, you know, lying somewhere like that, like bending further in. And so they might not lie on the same Cauchy slice. You're not guaranteed that. Now, what Aaron was able to prove using maxi-min is that if the boundary intervals are nested, then you can always put you can always find a Cauchy slice that contains all of those extremal surfaces. But if they're not nested, then in principle, anything can happen. Okay, so maxi-min. I'd like to think of this as version 2B of classical covariant holographic entanglement entropy. And this is by Aaron Wall.
Just a question. Do let me know if you're going to address this in 10 minutes.
Sure. And
I can stay silent.
Yeah.
Which is when you're saying that if they are nested, then you can't find the Cauchy slice that goes through all of them. But if you take any two surfaces, can't you just nest them by using like the interior of, like with the example that you found of R and R prime don't lie in the same surface?
Yeah.
Can't you use like R union R prime? And then R is in the R nesting.
So for R union R prime, you can find a Cauchy slice that will contain R and the larger surface. And you can find a Cauchy slice that will contain R prime and the larger surface, but you cannot find a Cauchy slice that will simultaneously contain all three.
Okay. That's weird geometrically, but okay, I believe that.
I'll see if I can find an easy to compute example where you can see this at work. I think potentially even in pure AdS, if you sort of find, if you take two intervals, one like this, and maybe one like that, then you're gonna have a problem.
Okay.
You can also, if you just take even stationary spacetime, like a rotating BTZ geometry, then the surfaces sort of wobble around from the rotation. So if you take the span of all surfaces as you move the boundary region around, it actually spans out the full volumes worth. So that's
okay. And
basically, it's just that the time like separated somewhere, as Netta was showing.
Yeah.
Okay. Thank you. That did help.
Okay, so Maximin, I want to emphasize, is not just useful for strong separativity. It's really valuable for proving a lot of things about holographic entanglement entropy. So it's a lot, I should say, it's a lot easier to compute things with the extremality formulation, and it's sort of a lot easier to prove things with the Maximin formulation. So they're both very valuable and for different purposes. So what is this Maximin formulation? So it comes as a sort of a procedure, rather. So the procedure is the following. So you pick some Cauchy foliation of your spacetime, and then you say, okay, on any Cauchy slice, sigma of the spacetime, where you require that your boundary region R lives in the boundary of sigma. This is actually something called restricted Maximin. It's a slight refinement of the original Maximin. Find the minimal surface, call it min sigma R, which is homologous to R. So in some sense, this is exactly what we did in the Ryutake-Yanagi case. You have some Cauchy slice, you find the minimal area surface on it. Now, find the maximal, it's Maximin, area surface over all of the min sigma R. So in other words, for every Cauchy slice, you pick a min, you find a min sigma R, and then you maximize over all of those choices. So if I have some set of Cauchy slices and each one of them I pick out, these are meant to all be, so this is the region R, this is again the region R. I'm not copying, I'm just showing the different Cauchy slices that I have. R, then I say, okay, which one of these has the largest area? So you find the minimal on a Cauchy slice and then you maximize over all Cauchy slices. So all Cauchy slices containing the region R. So basically the procedure looks something like max over Cauchy slices, and then you have min over surfaces in your Cauchy slice of the area. Okay, so this gives you the so-called maxi-min surface. So we call this the maxi-min surface. Then, under certain assumptions, something called stability, which I'm not going to get into unless you want to ask me during the Q&A, and then I'll be happy to get into it. This is the minimal area extremal surface homologous to R. In other words, the maxi-min surface is the surface that computes the von Neumann entropy, assuming the original covariant holographic entanglement entropy prescription was correct. The original HRT prescription was correct. So why is this so valuable? Well, two things. Really, there's one thing which is extremely valuable here, which is the fact that now you know that for your extremal surface that computes the von Neumann entropy, there exists a Cauchy slice on which it is minimal. Because by construction, the maxi-min comes from being the minimal surface on some Cauchy slice. And if you'll recall, in the proof of strong separativity, we used the fact that some of the surfaces were minimal on the Cauchy slice. We used minimality in order to derive a contradiction between 2 is less than 5 and 2 is greater than 5, if you recall. And so this gives you a way of doing the same thing. It tells you there exists a Cauchy slice on which a given extremal surface is minimal. And then you might hope to do something like strong separativity. And it does actually work. It's but what you need in order to make that really work, you need to be able to put all of the extremal surfaces that are under consideration, the ABC surface, the BC surface, the AC surface, and the C surface on one Cauchy slice. And this is something that is called the representative trick, which is also by Aaron.
Can I ask a question?
Go for it.
So these Cauchy surfaces are meant to be surfaces that we can place initial data on, right? And then evolve. Mm-hmm. So could we not take the surface that we find and evolve forward until we end up on this, the Cauchy slice that we wanted to compare the area to?
You could, but then the problem is if your surfaces don't lie on the same Cauchy slice, then you're not going to be. So put it this way: the critical ingredient for our proof of strong separativity was that all of the surfaces were minimal on the same slice.
Right. Right.
And so even if you, if your surfaces don't even lie on the same slice in the first place, how do you begin to compare the, where they're minimal?
Right.
So what this gives you is the fact that at least every one of them is minimal on at least one Cauchy slice. Mm-hmm. But you still have to find a way of mapping the other surfaces, this is maybe what you're suggesting right now, mapping the other surfaces to the same Cauchy slice in such a way that you actually know how the area changed.
Right, right.
Okay. And that's exactly actually what this representative trick does. So it doesn't evolve the data in the sort of way that you're suggesting. That's hard. It sort of circumvents it using the fact that we know how the area of an extremal surface changes as you evolve it along null rays.
Okay, sure.
So the representative trick, which exactly does that, is it's effectively a way of saying how to represent.
Excuse me, can I ask another quick question?
Absolutely.
Maybe a naive one, but it seems like, okay, these Cauchy slices are all space-like, and right? So yeah. This seems to imply that since you can find a Cauchy slice that contains the extremal surface, then also the HRT surface is space-like. And I wanted to know if it was obvious before finding this fact that HRT surfaces had to be space-like.
So it was obvious they had to be space-like, but actually what was not obvious is that they had to be achronal. So the distinction being that space-like means that there's a space-like tangent at every point, which is you feed that in the same sense that if you start out a geodesic equation, you give it boundary conditions that are space-like, then it's not going to change signature. You can prove this. An extremal surface also will not change signature, but it's possible for it to become chronal. So it's possible even though the tangent, so space-like is a local criterion, but it's possible for there to be 2 points which are very far away from one another that are on the extremal surface that are time-like separated. For example, if it sort of spirals around, and then you end up 2 points, we have 2 points that are time-like separated. Now, it also turns out that you can prove, certainly using the maxi-min formalism, I don't know if you can prove it using something else, that the minimal area one is not going to be chronal anywhere. But it's possible for just extremal ones to be chronal. There's sort of I mean, I'll stop there, but if you want to know more, I'm happy to talk about it more later.
Great, thank you.
Could I also ask a question?
Sure.
I'm a little surprised that to get the minimal area extremal surface, we take the maximum over the minimum. I would have maybe expected that we take the minimum and then the minimum again.
So if we take the minimum and then the minimum again, we're going to end up with a null surface with area 0.
Okay.
Maybe the way to think about it is the following. So let's think about geodesics. A space like geodesic is neither a global minimum nor a global maximum of the length functional, because if you think of it, it's a space like geodesic, you can always wiggle it a little bit in a time-like direction, and that'll reduce its length. And but the fact that when we talk about Euclidean spacetimes, then basically you can always increase its length because it's going to be a local minimum within the Euclidean spacetime, but you can always also decrease it by moving it in a Lorentzian direction.
Okay.
So space like geodesics are saddle points. They're not actual local minima or local maximum. And so we don't actually want the global minimum of the area functional. We want an extreme, we want a saddle point. And so we say, okay, we're going to take this to heart, that the surface needs to be sort of like a space like geodesic. It needs to be minimal in the space-like direction, but we need it to be maximal in the time-like direction. So we want to emulate what space like geodesics do. And
that makes sense.
Yeah, that's where this maximum intuition comes from.
Thanks.
Mm-hmm. Other questions? Okay, so the representative trick is a way of saying, okay, have some surface, it doesn't lie on this Cauchy slice, but I want to give it an avatar on that Cauchy slice. So how do we represent a surface on one slice on a different slice? And so the very rough idea, so if you have some surface, I have my XR over here, and this is the Cauchy slice that I want to map it to. So the idea is that you fire your light rays towards that Cauchy slice, and you consider this intersection, which we call X tilde R sigma, as the so-called representative. Now, I'm not going to go through the derivation of this here, but I did upload it to the website, so you can see the derivation there for why the area of XR is always larger than the area or equal to than the area of its representatives. This is only true for an extremal surface. It uses the fact that this quantity, the expansion, is going to be, the derivative of the expansion is negative, and the expansion is 0 here, and the expansion is the derivative of the area. So again, the details together with how this is used in a proof of, in order to prove causal wedge inclusion, are on the TASI website, on where my lecture notes are. So this is where, you can see exactly why this is true. So for now, for the lecture, I'm just going to say this is true. If you doubt it, go have a look at the lectures, the lecture page, and then and come ask me questions. But this is very valuable because it then allows you to compare different surfaces that lie on different Cauchy surfaces. And as long as you know that at least some of them are minimal on that Cauchy slice, then you can prove things like strong separativity. So this is a general sort of protocol for using maximin. So I'm just going to give you the algorithm. This is an algorithm that, in my experience, basically never fails. So the maximin proof algorithm. So one is you take the slice on which one of the surfaces you're interested in say XR is minimal. This is the HRT surface. You know it's minimal on some Cauchy slice. Let's call it sigma. 2. Now you use the representative trick to represent all other relevant extremal surfaces on that same slice. to represent, you know, XR prime, XR double prime, whichever surfaces you're interested in on sigma. So see if I can draw a picture that looks nice for this. So here we have R, and here we have our XR. And maybe we have another extremal surface, this, which goes sort of down below. And then we're going to map it using our null geodesics. We're going to map it back up to this slice. It'll have some. So this is, let's call this XR prime, and this will be XR prime sigma tilde. So now both of these lie on the same Cauchy slice sigma. And we can say, oh, I'm going to take this piece of this area and this piece of that area and add them up and use the fact that I know that XR is minimal on sigma. So use the facts that XR is minimal on sigma and that area of XR prime is larger, equal to area of XR prime sigma. And with this, you then say, okay, now play the same game as in the static case. So I'll show you how this works for strong separativity. It's sort of laughably easy once you're able to do this. I'm going to move this a little bit up without hopefully moving it totally out of your field of view. Okay, so for a strong separativity, we have the following extremal surfaces that we're interested in. We have X ABC, XC, XAC, XBC. These are the ones we're interested in. And we can put, as I mentioned, whenever they're nested, we can put them on the same, they'll be minimal on the same Cauchy slice. This is something you can prove. So that means that we can actually put XABC, XC, and XAC. All of these are going to be minimal on the same Cauchy slice. It's XBC that's going to be the problem. So here's what it looks like. So we have A, C, and B. And we have XABC. And we'll have XAC and XC. And the problem is going to be XBC. So XBC is actually going to be a representative. This is going to be XBC sigma tilde. And now we play exactly the same game that we played in the static case. We add up the different pieces and we say, okay, well, using the same game that we played in the static case, we find that the area of XABC plus the area of XC is less than or equal to the area of X tilde BC sigma plus the area of XAC. But we know the area of this is smaller than the area of XBC, right? This was the thing that I didn't prove for you, but you can check it out for yourself. This is then going to be less than or equal to area of XBC plus area of XAC. And ta-da, we have strong separativity. So here we use the fact that here we use the representative trick. And this can also be used to prove the sort of what we call entanglement wedge nesting, this type of trick. So we can also be used to prove that D of HR prime lies inside D of HR if R prime is inside R. So this is called entanglement wedge nesting, which means it's time for us to move on to discussing the entanglement wedge. But before I do so, let me ask if there are questions on the representative trick. This is something that I haven't seen any reviews of this, and I think it's one of the most useful things that we have in most useful techniques we have. So, questions?
So I may have missed it. How do we know that X, A, B, C, A, C, and C are all in the same cauchy slice?
Yeah, so I didn't prove this for you, but this is something that you can prove using the technology of Maximin, that if you have nested boundary regions, then all of the corresponding extremal surfaces are minimal on the same Cauchy slice. So I didn't prove this for you, but so if you want to see the proof for that, you'll have to look at Wall 2012, the Maximin paper where he proves this.
So I guess why could we not also say that ABC, BC, and C were on the same Cauchy slice? So just reflecting left to right.
So you could, but that Cauchy slice would not also contain XAC.
Ah, I see. Okay.
Yeah.
Thank you.
What was that?
I think two of us asked at once, but I was just curious. It seemed here that you got maybe lucky, or maybe it wasn't luck, that the representative trick inequality worked in the same direction as what you needed for strong subadditivity. Does it usually work out?
Yeah, it always works. It's kind of remarkable. It even works in the quantum case. So in the quantum case, you can do quantum Maximin, and not only will the representative trick work, but there you also have to account for strong subadditivity of the quantum fields in the bulk, which will still work the correct way for you. So it seems miraculous. I'm sure there's a deep reason for it, like maybe consistency of the AdS CFT dictionary.
Excuse me, can you repeat, please? How do you build the representative surface from the regional surface?
Sorry, can you just repeat that? You were cut off for just a moment there.
Oh, sorry. How do you build the representative surface starting from the regional surface?
Yes, of course.
Can you build that?
Yeah, sure. So the way that we build the representative, I'll actually draw a picture because I don't think I did. So if we have, we have some D of R, and we have some, so here's our XR. And we say, so this is, imagine a situation where it's causally, well, here's not causally separated, that's fine. And they say, okay, so here's some Cauchy slice. I would like to represent XR on this Cauchy slice. So what I do, I'm gonna fire a null family of null geodesics up to this, this Cauchy slice sigma. And then the intersection is the representative. So if I try to draw this in 3D, and forgive me if this does not come out very nice, but I'm going to give it my best shot. So here, something like this. This is sort of lined by geodesics. And this might be the new Cauchy slice, and then this would be, say, XR, and this would be XR sigma tilde.
Perfect, thank you.
Great.
Excuse me, doesn't that depend on which way you send the geodesics?
Very good. So I could also send them in this direction, but the magical thing about an extremal surface is that no matter which way you fire the geodesics, the area will still be decreasing.
Okay.
So it's actually immaterial for the comparisons that we want, which one we choose. Sometimes it's more convenient to choose one than the other.
Okay, but there's also in higher dimensions like a continuum of surfaces, not just two.
No, it's always two because there are only two normal directions, a codimension 2 surface, which means that you only have two linearly independent normal directions.
Okay.
Yeah.
Yeah, can I ask a question? Yeah, so is this like a Maximin proof of this strong subadditivity and like full generality? Because it seems that you emphasize that like this Maximin formulation is only true from the like compared to extremality formulation under certain like assumptions.
So this is the question of really how rigorous is the equivalence between Maximin and HRT. And I would say it's sort of physics level of rigor. There are some statements about existence and of the surfaces that are the requisite math theorems have not been proven. It's something called geometric measure theory, which is only currently developing some field of mathematics. So has it been shown on a very rigorous level that these two are equivalent? No. Has it been shown on a level that is very well motivated for physicists? I would say yes. Sort of depends on how much you're willing to say, okay, this is physics, so this is a very convincing argument, and how much you want to say, well, I want to make sure there are no gaps here.
Okay, thank you.
Sorry, Netta, I may have missed this. Do you need just the null energy condition for this representative trick, or any other conditions?
You need global hyperbolicity also, so that your null geodesics don't just stop somewhere because you excised a point. Yeah. So this assumes both of those. So for the quantum case, we'll assume the generalized second law, which the generalization of the quantum of the null energy condition. That we'll use that, but the same basic idea will also work for the for quantum maximum.
Great, thanks.
Actually, can I make one comment? Which is that you don't actually need to project along null congruencies. A completely different way would be to use maximin itself and project just in some time-like direction, because that's also guaranteed to be a smaller area than the extremal surface you're projecting.
That's right. Oh, well, so for the thing with the representative trick though is you can also use it for using the extremality formulation. So for causal wedge inclusion, you can use the representative trick without using maximin. So it's I find it better to use this, but it sometimes is inevitable and you have to use the maximin version. That's true. Yeah. Any other questions? All right. So I want to now actually finally define the entanglement wedge. We have a complete description of holographic entanglement entropy to leading order in any corrections. So they have the covariant version, we have the maximin formulation. And so it's time to define the entanglement wedge. We've sort of been using that term all along because I think most of you have seen it or heard of it before, but we should define it more rigorously. So given that we want to be able to compute the von Neumann entropy from the bulk, and given that we expect that when we say something is dual to D of R, it should be able to compute the von Neumann entropy minus trace rho log rho, then the sort of obvious conclusion, in retrospect at least, is that we should be able to reconstruct the entirety of the region that's between the extremal surface and the boundary subregion. So let's say, okay, everything that's between D of R and XR. But how do you make that covariant? Well, the way that we make it covariant is we say, okay, we should be able to reconstruct everything in the region between everything that's between here and here for any choice of Cauchy slice, which is another way of saying that we should be able to reconstruct the domain of dependence of HR, where HR is the homology hypersurface. And so this idea was first articulated by Van Ramstonk. And there was a nice paper by Bartek and others, and also by Aaron Wall, and finally also formalized by Hedrick, Hubani, Rangamani, and Lawrence, which is that this region really is the dual to D of HR. And I'll say more about what we mean by that in a moment. But fortunately, we now have a name for it, thanks to these folks, the entanglement wedge. Of R. So the conjecture is that we can reconstruct everything in the entanglement wedge. So some examples of the entanglement wedge. Well, we have some examples. So if we have two intervals.
Sorry, can I ask a question?
Go for it.
This may be a very silly question, but I think I missed it. What's the definition of HR? Is it the
homology? Is the homology hypersurface? Is the homology?
The homology of. Oh,
yes.
okay.
Yeah. Mm-hmm. So here, this is a homology hypersurface, and its domain of dependence will be the entanglement wedge. So in space-time, if we take, say, the Vaidia space-time, the entanglement wedge of the entire boundary is going to be literally the entire bulk. By contrast, if we take the long wormhole in AdS, which we can get by perturbing the thermal field double, where this is X, this is the extremal surface of one side, then the entanglement wedge will be this region over here, entanglement wedge of one side. Now, this duality, what we mean, well, we can ask what we mean by is dual to. And what we really mean is that we should be able to compute anything that we can compute using rho of R and operators that are localized to D of R. We should be able to compute using the entanglement wedge. And vice versa, things that are everything in the entanglement wedge, we should be able to compute, reconstruct using just the data on D of R. Now, there is the question of what do we mean by everything in the entanglement wedge? So what do we mean by everything in the entanglement wedge? Do we mean the equations of motion? Do we mean the metric? Do we mean quantum fields propagating? Expectation values of quantum fields propagating? So there's been progress on all of the above, on writing down an explicit reconstruction for all of the above. I would say the one that remains, in some sense, the most mysterious is the geometry itself. There's no sort of broad reconstruction for general spacetimes for any entanglement wedge. There are cases where you can reconstruct in certain types of spacetimes, or outside of the, or inside of the causal wedge, but not inside of the entanglement wedge. And so in some sense, I would say this is the most open, although it certainly is not true that we in general know how to recover the equations of motion. There's been some progress in getting them in linearized equations of motion into second order around pure AdS. There's been the most progress on this bit over here, but a lot of these questions are still somewhat mysterious. Although I think that in some sense this is the most well understood. So I will talk more about reconstruction and why we think we can reconstruct the entanglement wedge. It's a very beautiful proof by Don Carlo and Wall. And even though I won't give you the proof, I'll sort of try to give you the flavor of it. But before we can go there, we actually have to talk about quantum corrections, because all of this makes a lot more sense once we start adding quantum corrections to the game. So this sentence concludes the classical interlude, and we're going to move on now to quantum corrections.
I have a question.
Yes, absolutely.
So the entanglement wedge, like if you're thinking about I guess a static black hole space-time, it doesn't extend into the horizon, does it?
For a static black hole, like static Schwarzschild, for example,
yeah,
the causal surface coincides with the extremal surface, so it's everything outside of the black hole. But as soon as you slightly perturb the black hole, then part of the entanglement wedge will be behind the event horizon.
Okay.
Other questions?
It's one question, sorry. The fact that you can have part of the entanglement wedge behind the horizon tells you, does it tell you anything about how difficult it is to reconstruct outside or inside? And is there a reason why reconstructing inside should be more difficult than reconstructing outside from this point of view?
Yeah, so you're talking about reconstruction complexity. This is another case where I would say, just get a better idea of what's happening, we have to talk about quantum corrections. And so I'm going to take a pause on your question until the next lecture, where I will address it then. So quantum corrections. holographic entanglement entropy. So how does the holographic entanglement entropy formula change once we start adding quantum corrections? And there's a sense in which the absolute simplest thing to, simplest answer that I can give you is, well, okay, if you work in the limit where your quantum fields are propagating on your curved spacetime, but they're not back reacting on it. So our metric is fixed and classical, which has some quantum fields that are propagating on it. Then you can basically repeat the Lefkowitz-Maldacena calculation with just a one loop effective action. So at that point, you're just going to include the contribution from the matter, but you're not going to worry about any modifications to your gravitational action. And with this kind of just say, and here's what you get. I can tell you what you get when you do that. So first order corrections. And I'm also including higher derivative corrections in this. I'm sort of going to do both at once, but primarily because when you include the one loop effective action, you end up incurring some higher derivative subleading corrections. So, so this is Faulkner, Lukowitz, Maldacena, and there was also a lot of work on higher derivative corrections by Shidong. So S of rho r is equal to what I'm going to call the generalized area of xr over 4g plus S of rho hr. So let me parse what this is. First of all, xr is the same surface that we had before. It's the minimal area, extremal surface homologous to r. Nothing in that has changed. So xr is as before. Now, this is now an A-gen as opposed to an area. So what do we mean by a generalized area? Essentially, it's just like the area functional, but now instead of just containing root h, it receives higher derivative corrections. So you've already seen, I think sometime last week, you saw this story about the walled entropy, and how you get the sort of the area term becomes an S walled or S grav term, which has higher derivative corrections. Now, this is not exactly the walled entropy. And the reason is that the walled entropy is something that is valid when you have a stationary horizon. And there are various terms that drop out of the walled entropy. When you do the calculation for this gravitational action, when you include higher derivative corrections, there are various terms that drop out when you are considering a stationary horizon. So here we're not working on a horizon at all. We're working with an extremal surface. And so we don't actually end up with just the walled entropy. We end up with the walled entropy corrected with various extrinsic curvature terms. So it's very similar to the walled entropy. So this is so A-gen is a higher derivative corrected area. Which is a walled entropy like, but with higher derivative, with extrinsic curvature corrections. And I can refer you to the various literature on the subject that gives you the form of these extrinsic curvature corrections. Now, what is S of rho HR? So S of rho HR is the von Neumann entropy of the bulk quantum fields in the entanglement wedge. And so this altogether gives you the first order correction to holographic entanglement entropy. Now, this combination of terms has a name. It's called the generalized entropy of the surface XR. Now, one question that you may or may not be worried about, so actually, let me draw a picture and then maybe you'll start worrying about it. So here's my region R, and I can draw my XR. So my rho HR is evaluated here. Now, you might say, well, hang on a second. Before, all the divergences matched up, right? We had this divergence across the UV divergence in this, which matched with the IR divergence. We put in a small cutoff over here, and then we took the large C limit, which is the same as taking the small GH bar limit. But now we have this thing here, and isn't this also UV divergent? But this time with the bulk UV, this thing is UV divergent, so it's cutoff dependent. How is this possible? How could this possibly be well defined? And what I personally find kind of miraculous is that the generalized entropy is a very special quantity. And there's very good evidence now to suggest that, in fact, the divergences and anything that's cutoff dependent in this piece here gets canceled out by renormalization of Newton's constant. And so what it appears to be the case, and it hasn't been proven in broad generality, but it's been proven for certain classes of fields, that this quantity appears to be independent of the UV cutoff, of the bulk UV cutoff. And so that, in general, to me, that suggests that the generalized entropy is actually a very fundamental object in quantum gravity, that we're very short on things that are UV independent, UV complete in the sense you could think of it. So even though this might have been a worry, in fact, we expect that really it shouldn't be. So this is a very natural thing to worry about, but we think that the counter terms cancel out and everything balances. And so this thing is really independent of the bulk UV cutoff. And in fact, Faulkner, Lukowitz, and Maldacena didn't discover the generalized entropy. This is something that was around in black hole mechanics for a very long time. So it was dubbed the generalized entropy actually by Jacob Bekenstein. So it's worth taking a little bit of a trip back down memory lane for this. So if you recall, Jacob Bekenstein was the one who initially proposed that there was some kind of a gravitational entropy, and that was V0 of holographic entanglement entropy. And but you'll recall his reason for doing this, other than the fact that he had a not very nice PhD advisor give him a hard problem, was that he wanted to explain the apparent violation of the second law of thermodynamics. And for that, what he really needed to show, so for Bekenstein, the important point was that the total sum over constituents of the universe, the total entropies over constituents of the universe, this thing, that this does not decrease with time. And so how can we rewrite this? Well, in terms of black holes, we just say, well, this then is going to be S of the black hole, which is a gen over 4G, plus S of the matter outside, which is, of course, just the generalized entropy of the event horizon. So this was the context in which the generalized entropy was first defined, and also the context in which Bekenstein said, okay, well, this must be a law of nature, that the generalized entropy in the universe does not decrease as a function of time, the generalized entropy of event horizons. So when I say of an event horizon, I mean that in Bekenstein's formulation, the surface XR is a cross-section of an event horizon. So what we're talking about is, so here's an event horizon. We're talking about some surface here. This is where we're evaluating. This is S matter outside. And this is where A gen is being evaluated. So this was what was important for Bekenstein, and he proposed what's known as the generalized second law. So generalized second law is the hypothesis that, excuse me, dd lambda of the generalized entropy of an event horizon is greater than or equal to 0, where lambda is a parameter along the event horizon. And this, in fact, this is what we typically use instead of the null energy condition in cases when it's violated due to quantum fields. So many of the proofs that we like in GR, including proofs of strong separativity, including the proof of entanglement wedge nesting, of causal wedge inclusion, rely on the null energy condition, which breaks down when we leave the classical regime behind. And we have to replace it with something. And so the assumption that we typically make is the generalized second law, which hasn't been proven in broad generality, but it has proofs in many different regimes. And there's a very nice review of the many different proofs by Aaron Wall. And I think some of the original proofs you can also find in a paper by Solidukin. So this is, yeah.
I was just gonna ask, you mentioned before, and maybe you'll say it in a bit, but you mentioned the back reaction of the quantum fields on the geometry. Does that have a contribution to the entropy? And if so, is it finite?
Yes, so how do we talk about the back reaction? So typically the way we talk about the back reaction is we say, okay, we have some metric. So GAB, this is the metric in our space-time. And there's some contribution. So this is the classical metric called JB0. So sort of first zeroth order in perturbation theory in GH bar. And what we do is we take this metric and we plug it in. So we have some quantum fields that are propagating on it. Now these quantum fields have some stress tensor, and we can plug that stress tensor into the Einstein equation. So we'll have GAB equals 8 pi TAB, and this TAB will be now an expectation value. That will give us a correction to GAB0. So we'll have some first order correction, which is sourced by the stress tensor of the quantum fields. Well, now we can actually, so now we have a new metric. We can resolve the field equations for the matter fields. We get a new corrected stress tensor. We plug it back into the Einstein equation, and we get more corrections to this. So the back reaction of the quantum fields comes in, basically at every stage of the game. It will change them. It will modify the entropy. It will also modify the area. But of course, that only matters if we're working to more than first order. We have to work beyond first order, which is actually a great segue into the next part of this lecture, which is what happens to the holographic entanglement entropy proposal at subleading orders. Now, there is real reason to worry here, which is that at zeroth order, so at first correction, we have quantum fields propagating on our space-time. They don't back react on the metric. And so that means in particular that RAB, KA, KB is still greater than or equal to 0 if quantum fields do not back react. So that means that the Faulkner-Lukowitz-Maldacena prescription is fine in terms of strong separativity, in terms of causal wedge inclusion, it's fine. But as soon as we allow back reaction, we run the risk of violating this because we know that the null energy condition can be violated by very pedestrian quantum states. And we know it's also violated by not so pedestrian quantum states like Hawking radiation, but it can be violated by states that have a Casimir. Basically, things that we expect do happen. Localized negative energy will violate the null energy condition. And so that is very worrying. Now you could say, well, you have this great generalized second law. Why not use that instead? Well, the generalized second law is very nice. And unfortunately, it applies to causal horizons. And in particular, it tells us how the generalized entropy of a surface changes. But all we know about the extremal surface is how its area changes. We only know the change of the first piece of it. We don't know what happens with the other, with the rest, with the Bonoman entropy piece. So how are we supposed to prove things like strong separativity about a classical extremal surface when the only control we have over it is over its area? And what we really need in order to apply something like the generalized second law is to have control over how its generalized entropy is changing. And so the the upshot of this, and this the way I'm telling it to you is exactly the way that this this developed. So Aaron Wall and I were worrying about this, and said, okay, well, maybe it's not the classical extremal surface that's the relevant one once you include back reaction from bulk quantum fields. And so what we said, and this is the V3 of holographic entanglement entropy. So this is me and Aaron. This is meant to be to all orders in GH bar, including any order of back reaction. So this is both covariant and any order in GH bar. We said it makes a lot more sense to extremize the same thing that you're calculating. So we proposed that the von Neumann entropy of the density matrix rho R is given by the generalized entropy of a surface chi R, where, so this is to all orders in GH bar, where chi R is the minimal S-gen quantum extremal surface. I'll explain what that means in a second. Homologous to R. And quantum extremal surface means that it extremizes the generalized entropy instead of the area. So it means that if you vary S-gen with respect to any normal direction to the surface, this is going to be 0 for all NA normal to chi R. Now, there are some subtleties in exactly how one is supposed to interpret this. And I'm not going to go into them because you could say, oh, you know, you're varying this in the time-like direction, and that's complicated because you have to vary this non-local quantity. You can make all of that precise. And I can give you a reference where we made this precise for time-like variations. But I would say more intuitively, there's very beautiful formalism by Busso et al. For null variations. So this is in some sense a lot more useful, because for null variations, you can use something like the generalized second law to compare with something like the causal surface and prove causal wedge inclusion. So quantum extremal surfaces are kind of weird in the best way. We thought we understood them, and they already sort of, even when we first proposed these, they presented a lot of strange behaviors, but very exciting. In the past couple of years, they've shown up as being even weirder than we thought, and giving us even more insights than we could have possibly expected. So a couple of comments on why quantum extremal surfaces are weird and what you can and cannot do with them. So to begin with, you can prove causal wedge inclusion for quantum extremal surfaces using just the generalized second law. So properties of quantum extremal surfaces. So the causal wedge inclusion, the proof works almost identically to the classical proof, which you can find on the web page, except instead of the null entropy, you put in the generalized second law. So that's the first thing that we have to use. That's the first property that we have. Now you can also prove strong subadditivity, but for this you need a quantum maxi-min formulation, which does exist. So this is something that you can formulate, and then strong subadditivity works in the same way except instead of just adding and subtracting areas, now you also need to add and subtract entropies. And in order to prove strong subadditivity for the generalized entropy, you have to use strong subadditivity of the bulk quantum fields, so that the bulk von Neumann entropy also satisfies strong subadditivity. Now, there is a very interesting property of quantum extremal surfaces, which is dramatically different from their classical counterparts, which is the following. So it is not the case that chi-r equals chi of the complement of r. Not always, it's not necessarily true. It can be true, but it's not necessarily true. So let's recall, in the classical case, so we have some circle here, and we have some r and r bar. And we say, well, okay, if this thing is the minimal area extremal surface homologous to R, then it's also going to be homologous to R bar, and it's the minimal area surface. So XR equals XR bar. Otherwise, if they weren't equal, then there would be another extremal surface here with smaller area, and then that would be the extremal surface of R. So this always has to be true. It's kind of obvious. Extremality is just local to the surface. It doesn't care which side you're evaluating it on. This is not true in the quantum case because now we're evaluating an entropy, and it matters which side we evaluate it on. So, quantum case. Suppose we have some, and the same thing, we have an R and R bar. And here, let's say, is chi r. Well, initially, suppose we start out, okay, so the thing is, this is what's going to turn out to be the case is that this is true chi r equals chi r bar whenever the bulk state is pure. But if the bulk state is mixed, then it does not have to be the case. So if the bulk state is mixed, then the von Neumann entropy of this will not be the same as the von Neumann entropy of the geometrical complement. So let's call this rho HR and rho HR bar. And so what we have is that if the bulk state is not pure, then it does not need to be true. It's not going to be true that these two are equals. And that also means that their gradients are not necessarily going to match. And so the derivatives will not change, will not match. And so this can be quantum extremal when evaluated via this entropy, but not quantum extremal if it's evaluated using this entropy. So a surface can be R quantum extremal without being R bar quantum extremal. And so what, yeah, question?
Oh, I was just gonna ask, so they don't have to be equal, but do they always overlap, or can you have situations where you have some like gap that you can't get to?
Yeah, so generically you will have the gaps. They will not overlap. So if they're not the same, that you can prove using quantum maximin that they're not going to overlap. So the situation, if you have a mixed state in the bulk, will look like this. So this is chi r, this is chi r bar. This is the entanglement wedge of chi r. This is the entanglement wedge of chi r bar, and this is in no man's land. So this is right quantum extremal surface. This is left quantum extremal, and then you have this region in the middle here, which does not belong to either one of the two wedges. And of course, the entanglement wedge reconstruction suggests that the natural thing to do is to somehow associate this to the purification of the mixed bulk state. Now, my suspicion is that Ahmed is going to talk about this a lot next week, so I won't belabor the point, but it's really this, this phenomenon that the left and right quantum extremal surfaces, the R and R bar quantum extremal surfaces, need not be identical. That has sort of resulted or given rise to our ability to compute the page curve and all the recent developments on the black hole information paradox, sort of catalyzed by the realization that there's this no man's land over here that, that is due to the fact that the quantum extremal surfaces do not have to line up.
Sorry, so if you do try to like purify that bulk state and you add an extra system, like it's not in your space-time, so there's just no way to interpret it, or?
Well, so there's the question, okay, if you have some purification, is the purification dual to this? What if the purification is I don't know, a banana? What if it's, you know, some, does that mean that you have a dual to this region over here? That's a good question. It's, so let me pause on that, and we can talk about it more in the Q&A, because technically speaking, this is a question that's very important in the case of the black hole information paradox, and really the first case where we've seen that there's this very large macroscopic gap. There was an understanding before that we thought that the gap would always be small. And working in perturbation theory, turns out that this doesn't have to be the case. But we think now that the gap is going to be dual to the purification, even though the purification is not in R or R bar.
Thank you.
Actually, I have a question about that.
Yeah.
The region you drew in the middle with the question marks would still be in the entanglement wedge of R union R bar, right? Or no?
Well, that would strongly depend on whether the empty set has a smaller von Neumann entropy than the generalized entropy of this together with that. So if it's not the case, then that will not belong in the entanglement wedge.
Great, thanks.
Excuse me, about that, if that's the case, and so if the sum of these two extreme quantum set surfaces actually have a smaller generalized entropy than the empty set, then it means that you can, given your theory on the boundary, you can just not reconstruct the two theory in their region. And in order to reconstruct that, you need to have, because in some sense you have a CFT state which is also not pure, and you need to have a purification of the CFT state.
That's right.
And that's why you need to reconstruct the bulk. So it means that the bulk knows more than the CFT itself knows.
Well, I would be careful with that. It's the particular state that we're working with in that CFT. So the particular state we're working with is not a pure state. So you could say, oh, we didn't describe the entire system. And it's our fault. It's sort of the same as saying, oh, what if I only gave you R bar? Then you can only reconstruct up to here. But it's not like the CFT doesn't know about the rest of it. It's that I only gave you part of what I was supposed to give you. I didn't give you all the information.
Okay, because I'm generally, like, I tend to think about, I have a geometry that corresponds to a specific state of the CFT. But in this case, it seems like you have a geometry, and a part of a geometry corresponds to a specific state in the CFT, but you have another part that corresponds to a purification of the state in the same CFT. It seems like it's smarter, the bulk is smarter than at least of the state of the CFT.
Of this piece of the CFT, but you've seen it before, like with the thermal field double. If you only take one of the two CFTs, then you don't get the entire bulk. But if you take both of the CFTs, then you get the full bulk. It's very analogous. There's some additional piece that we have to add into the system in order to get everything.
Okay, that makes sense.
Other questions? Let's see if there's something
Can
I want to. Oh yeah, go for it. Mm-hmm.
May I ask a question?
Sure.
So how does this picture kind of look when you were to consider, say, a Vaidya space-time? I know Vaidya is a bit funny, but so there you said that the entanglement wedge was, well, basically the
entire space-time, yeah.
Right.
Right.
So now what happens when you go and you do this with this quantum null surfaces, or this quantum extremal,
So for just Vaidya, if you're not doing anything funny to it, if you're collapsed some pure state into a black hole, then the bulk is going to be pure, and the von Neumann entropy of the empty set will be 0. So that the area of the empty set plus the von Neumann entropy of the empty set will be 0. and you will still have the empty set as the minimal quantum extremal surface. And so the entire bulk will still be in the entanglement wedge. Now, if you were to do something funny to Vidya, if you were to prepare it and then say extract some of the quantum fields from it, if you were to say couple it to a reservoir and allow it to evaporate, then things get interesting, and eventually what happens is you get a new quantum extremal surface, which is smaller in generalized entropy than the empty set. So if you sort of have a pure state from the beginning to end, then nothing funny is going to happen in Vidya. But if you allow yourself to do something like coupling it to another system, so that you start up with a pure state and then eventually the state becomes mixed, then you can get something non-trivial happening, like a new quantum extremal surface, which is more minimal than the empty set.
Sure. I guess I was just wondering if you end up finding something funny, like you can understand, or you can reconstruct what fell into the Vidya black brain, say, or black hole, whatever you choose.
Well, yeah. So then, essentially what you get from that is, if you allow the Vidya black hole to evaporate into an external system, what you find is that you end up with this gap region, and the gap region is, you expect to be encoded in the radiation that was extracted into the reservoir, and then you expect to be able to reconstruct everything that was inside, using the radiation. Now, I mean, this is related to this all these recent page curve calculations, but which touches upon all the black hole information paradox stuff that you're going to learn about next week. But the rough idea is it's very similar to this. And once you add in the auxiliary system, then you can reconstruct what was here. But before you add it in that case, the auxiliary system is the Hawking radiation. Before you added it, then you are not able to reconstruct that.
Thank you.
I also have a question.
Okay, let me just, so I think the Q&A session has already started. I just want to say one thing, and then we'll do straight into Q&A. Is that okay?
Yeah.
Sounds good.
Okay. So I just wanted to wrap up. So at this point where we stand, this formula, the generalized entropy of the quantum extremal surface, appears to be the most up-to-date version of holographic entanglement entropy. And we define the entanglement wedge not in terms of the classical extremal surface, but in terms of the quantum extremal surface. So the entanglement wedge is the domain of dependence of HR, where this is the homology hypersurface for the quantum extremal surface. But the one caveat I want to draw here before I close is that there has been some recent work studying mixtures in the bulk. So situations where the bulk matter, it looks something like this. And then, so this is by Akers and Pennington. And then it appears that you do need to potentially slightly modify this. It's not 100% clear yet what is the right modification, but it is clear that it does have to admit some kind of modification when you're looking at states that are mixtures like this. So this is a paper from 2020. Okay, so next time we're going to talk about reconstruction and complexity of reconstruction, all in 75 minutes. All right, now we can go back to questions.
All right, thank you.
So I have a question. Mm-hmm. Purifications in general are not unique. Mm-hmm. So if you purify a state and then you say that's going to correspond to a particular bulk configuration, does that somehow mean that so the no man's land that you have in that diagram, there's not a unique choice for it because there's not a unique purification?
Well, so in some sense, it depends. If you prepared this, if this is the result of some dynamical process that started out in a pure state and end up in a mixed state, and you'll never hear me say this because I'm a staunch believer in unitarity, but suppose that you had a process like that. You start in a pure state, you end up in a mixed state, then you would expect that the the purification, there's a unique purification that, that there's a unique system that gives you this if you believe that there's some kind of a deterministic way that this happened. Now, how might this be the case? If, for example, you were to couple your system to some other system, and then you said, okay, now my bulk is an open system, the evolution of the two of the, this auxiliary system and my bulk is unitary together. And so there's some deterministic evolution that gives me the entire system. And in that case, you do expect that there is a purification that corresponds to this, and that purification is determined by the evolution of the bulk. Now, more generally, if you just kind of prescribe and say, okay, I have a mixed state and this is all there is, then there is a level of uncertainty as far as what can possibly, go in this in-between region here. And you can think of it in some sense this way. If I only give you chi-r bar, and I don't give you chi-r, then I don't know what chi-r is. And this, what the bulk in the entanglement wedge of chi-r will depend on the CFT state describing it. So if we think there's a duality between this and some purification, then what happens here will depend on the purifier system. And so but this means that this is consistent with multiple possible purification systems just based on what you know from here and from here.
Okay. Thank you.
Other questions?
I guess I have a question.
Mm-hmm.
So in terms of so you said that we know pretty much that any operator can be reconstructed from bulk field can be reconstructed in the entanglement wedge. And then you said that it was a bit more uncertain for the metric and things like that. So what would be the state of the art about that?
So I would say that if you're looking for broad generality, basically, if you don't want to make any assumptions about symmetries in the space-time, and you just want to say, all I have is a CFT state, and I want to reconstruct the metric, I would say we don't have anything. But then you say, okay, maybe I'm willing to give us a little bit of room. Maybe I'll say, I don't know about the space-time, but here's something that I do know. I know that there's no phase transition in the von Neumann entropy in terms of, as I take the region R and I increase it to some region R prime. So this is something you can say, okay, suppose I know that. So that tells us that, okay, in the bulk, then the surfaces continuously interpolate. There's no jump. And then in 4 dimensions, there is a proof by Ning, Bao, and friends that in that case, it is possible. So in that case, there exists a unique metric that that corresponds to that if you know that you can fix a unique metric if you know those areas. It's not constructive, so it doesn't tell you that. In fact, it doesn't tell you that that it exists. It tells you that if it exists, then it is unique, but it doesn't tell you how to get it. So so there you're sort of you're a little bit you're out. I mean, I would say you're out of luck. It was a significant advance forward, but and that is purely classical. It's on classical extremal surfaces. It uses something called inverse mean curvature flow, which is something that we understand well classically, but there's been a lot of mathematical work on it, and mathematicians typically don't care too much about quantum extremal surfaces. If you say something else, if you say, okay, here's, I want broad generality, but I'm willing to say I only want the metric in the causal wedge, and in the causal wedge of the entire boundary. Then there's the light cone cut approach. So Gary Horowitz and I give a prescription. So that is actually prescriptive for getting the metric up to an overall function. So it's not the full metric, it's the metric up to an overall rescaling, so the conformal metric, using the D+3 point correlators in the dual CFT. It's purely classical again, and it only works in the causal wedge. It's a very causal construction. So it is doomed in the entanglement wedge, which is not to say it's not valuable, but it's not going to help you there. If you're willing to impose other symmetries, there are other constructions. But basically, if you're asking what's the general take, I don't know. I don't think we have one. And certainly not when you have quantum fluctuations and you're talking about quantum extremal surfaces, then I don't know of anything that we might use.
Maybe just a small comment on that. So you can use the entanglement entropies themselves, again, as Netta said, in some specific situations. So you could use comparison of the extremal surface areas for nearby extremal surfaces and get insight possibly up to the real extremal surface. So the entire and part of the entanglement wedge up to the extremal surface. So if you have, for example, static spherically symmetric spacetime, then you can do it explicitly, as Sam Wilson and John Hammersley have done a while ago, and so forth. So there's lots of works on that are constructive. So that was just
lots of corners, yeah. But if you're looking for like a general construction, I think there is not one. Yeah. In 4 dimensions, at least without space transitions, we know there should be one. But I mean, some people even ask the question: is the metric generally reconstructible at all, or do we only have a hope with the quantum fields? I don't subscribe to that to those doubts, but I have heard those expressed.
Great, thanks.
Other questions? There's so many questions in the 10 minutes before I finished, and then no questions afterwards.
Okay, well, maybe we can go into the informal part.
Yeah, let's do that.
People ask offline.